Hi, I'm Omico Wang from Kuaishou. We broke a Kotlin native constraint to run Kotlin Multiplatform at massive scale. And AI is now accelerating our migration. Real problems, real solutions. Here's where we are headed. Before we dive in, let me quickly introduce myself. I'm on the Kuaishou app infra team, where I've spent most of my time on our KMP migration and develop tooling that supports it. If you would like to keep the conversation going, find me on GitHub or Kotlin Slack. Kuaishou is one of the largest short video platforms in the world. 3 revenue channels: marketing, live streaming, and economics. As of fiscal year 2025, we serve over 400 million daily active users and more than 700 million monthly active users. Our mission is simple, on purpose, to help people discover their needs and use their talents in order to find their unique band of happinesses. Here, what we will talk through in 4 parts. The first 2 is about share some contexts on Kuaishou. The last 2 focus on the problem we actually hit, how we solve them, and where we are headed next. So let's get started. As I mentioned earlier, we serve a massive user base. We release new features and challenges every week. Our Android, iOS, and KMP codebases are 3 separate repos, and they must remain highly synchronized to ensure constant releases, which I will explain more later. Our codebase is 15 years old. Paying down accumulated technical debt isn't a one-off project. It's a fight that never stops. The numbers tell the story. On each platform, our codebase has long since surpassed 10 million lines of code. On the Android platform, more than 4 million lines of code are still written in Java. In addition, given our current infra, we are also continuously upgrading our Intel toolchain. Our AGP version is still stuck at 7.0, which makes me a newbie very stressed. On iOS, 99% of code is still Objective-C, and we have no plans to migrate to Swift. And we still rely on the Coconut pods. Now, multiply that across many teams, many repos, and coordinations gets extremely hard. Also, we use compose multiplatform in selected scenarios. So my team focuses on the KMP migration. We built a lightweight platform adapter layer on top of the shell KMP, so native UIs stay in sync and the teams can move without rewriting everything at once. Next, how we organize KMP engineering at Kuaishou, and then the concrete pin that structure has to observe. This slide shows how KMP is wired into our Android and iOS app, and how our R&D system spans. The last slide was the overview. This is what still hurts day to day. Dev tooling, build and merge, production, observability, simping engineering feels everyday week. Let's talk about what we did next. So for the KN artifact splitting, before we get into the breakthrough itself, let's take a quick look at how our repos are structured. We run 3 repos on purpose. KMP ship as artifacts. Each app consumes them separately and move at their own pace, but logic stays shared. Now we get to the core technical problem. KN has a fundamental constraint that compiler can only produce a single framework. As the Kotlin documentation shows, feature modules are all merged into one umbrella artifact. That single artifact blocks independent module dependency management, prevents independent publishing, and creates several compile time bottlenecks. That wasn't as the codebases grew. Let me give you the concrete numbers. All of our KMP code was centralized in the KMP client repo as one giant artifact. This caused iOS release compile times to exceed 40 minutes. The generate object C header file had over 63,000 lines. Every single API change triggered recompilation of over 3,000 files. Taking about 30 minutes, native SDK teams had to pull the entire KMP artifact, even if they only need a tiny fraction of it. Our goal was clear. From the start, we needed to achieve 5 dimensions of independence. To get there, we need KMP SDK independent publishing with multi-artifact splitting. This was the problem we had to solve. The first challenge is KN runtime binding. The compiler must merge runtime BC into every binary singletons, and the thread local storage hold internal states. Link tools SDK that each ship their own runtime, and you get the states corruption and crashes. The merge step is first. There is no opt-out. We stripped 3 redundancies. At final link, one runtime for the whole app. Each SDK contributes only its own code. The second challenge is LTO symbol visibility. With LTO on, the internalized path turns public symbol internal grid for one binary, fit for split SDKs. We got undefined symbol errors. Our solution is LMVM use whitelist injection. Public APIs are multiply linkable, while internal symbols are still processed by DCE to achieve optimal size. The third challenge is cross-module duplicate symbols. Link several independent SDKs into one app and you get 2 link visuals. We ship in layers, standalone keylabs, and static frameworks, so native teams depends only what they need. So what did we achieve? At our scale, we broke KN single artifact constraint. 2 changes, independent KMP SDK releases, multi-artifact split in the main repo. This is independent delivery from dev to ops. This is not just some kind of optimization, but a necessary requirement for KMP to organizations of our size. Now let's shift to AI infra. As you can see, we use different workflows in different scenarios, which is legacy code migration and new features. Due to the time limitations, we only focus on the legacy code migration workflow today, which I take full responsibility for it. Thanks for the great work that Meta and Uber did and shared. We implemented our own migration platform by referencing their solution. Our J2K migration tool is called Kuaishou. It is an IntelliJ plugin built for 2025.3 with K2 compiler enabled using the Kotlin Analysis API. It converts Java code to Kotlin and serves as the front-end for K2 KMP AI-assisted migration workflow. We learned earlier that convertible is not the same as migratable. The default IntelliJ J2K output often within no ability to aggressively ends up with defensive non-check boilerplate. Our solution is nullability explosion is annotation injection. In this simple, before conversion, we inject not known annotations from the framework context, so Kotlin signatures stay clean and as shown. In the past, we maintained pattern-specific rules by modifying PSI. It's costly and has to scale. Now, thanks to AI, we iterate quickly with an agent skill, then codify stable scenarios into PSI, lowering development and maintenance costs. This slide shows a subset of the rules we codified in our PSI automation and agent skill. We are short on time, so I won't walk through in the detail here. In Kuaishou, I also implement export of source file metadata. We collect it right after project sync directly via the IntelliJ API. Like the J2K workflow, we expose it through MCP so agents can use it. That piece belongs to K2 KMP. Looking ahead, we see three priorities. First, shorter KN feedback loops. Second, agentic governance. Third, the next bottlenecks. Our goal is simpler infra with AI woven through the Intel R&D life cycle. So thank you for listening today. You can find me on GitHub and Kotlin Stack. I'm always happy to continue this conversation or answering questions. Thank you.